Okay, so we want to figure out how much force power Yoda can exert. There was a couple of kind of people who had tried to figure out, how if you could put Superman on a generator, could he power the whole world, kind of thing. So we're going to do this with Yoda. Okay, so Yoda's greatest display of raw power in the original trilogy. Okay, before Star Wars sucked. Okay, yeah. So before that, okay, his greatest display of raw power was that he lifted Luke Skywalker's X-Wing out of the swamp on Dagobah and set it down to prove to him that size matters not. Okay, so what I'm going to do is I'm first going to show you that video clip, and then we're going to calculate how much power Yoda has based on what he did, okay, during that display of power. Okay, now, the clip I'm going to show you is during Luke Skywalker's training on Dagobah. Okay, it's also one of the most important moments in Star Wars because it is where the nature of the Force is explained for the first time. And then after that, it's just like bastardized. But whatever. Okay, it's the first time it's explained, and it's explained really well. Okay, so we've now seen the video where he lifts the X-Wing out of the water, okay, and moves it over, kind of just makes it fly horizontally and then sets it down. Okay, all right, so as far as physically moving objects goes, okay, this was easily the biggest expenditure of energy through the Force that we saw from anybody in the original. Okay, now the energy it takes to lift an object, okay, to a specified height is equal to what? How do we calculate something's potential energy? With science, yes. What's the formula for potential energy? mgh, right. Okay, so we take the object's mass, right? We multiply it by the acceleration due to gravity, okay, so 9.81 for us, okay, and times the height that it's lifted. Okay, so the X-Wing scene lets us use this to put a lower limit on Yoda's peak hour power output. Now, this is where it gets really geeky. Not that it wasn't already, but it gets even more so. Okay, so an X-Wing's mass has never been canonically established. That means, like in Star Wars canon, which is like things that Disney says are true about Star Wars, the mass of an X-Wing has never been listed. All kinds of crazy things are listed, but that has never been. So instead, okay, we do know that its length is 12.5 meters. Why that's listed and not its mass, we don't know, but it's 12.5 meters long. Okay? An F-22, which is a real fighter aircraft, is 19 meters long and weighs 19,700 kilograms. So we'll scale down and say that the X-Wing is about 12,000, well, that has to be kilograms, okay, not pounds, kilograms, okay, or 5 meters, somewhere around that. Sorry, 5,600 kilograms. Sorry, 12,000 pounds, 5,600 kilograms. So we're going to go with the mass being 5,600 kilograms for the X-Wing. So now we know mass, okay? But this is on Dagobah, not on Earth. I have no idea what the acceleration due to gravity is on Dagobah, okay? So we need to know how fast it was rising, okay? So we can figure out how high up it goes. So this guy who made this thing up, because it wasn't me, like I'm geeky, but this guy's like way beyond anything. Okay, so the front landing strut, okay, that we saw come out of the water on the landing gear, okay, rises in about 3.5 seconds, and he estimated the strut to be 1.4 meters long, based on a scene from Star Wars: A New Hope. That's the original one, where there was a person standing beside it. This is how much effort this guy put into this. Okay. All right, so in A New Hope, where crew members squeeze past it, which tells us an X-Wing is, we can figure out how fast it's rising. It rose 1.4 meters in 3.5 seconds. All right, so we'll just quickly do that calculation here. Okay, 1.4 meters divided by 3.5 seconds. All right, so the speed it's moving at is 0.4 meters per second. Okay, and lastly, we need to know the strength of gravity on Dagobah. We said this is going to be the problem because we don't know what it is. Okay, I don't know how we do that, but apparently there's this website called Wikipedia. Yeah, like you'll never think I'm a geek again after this. Okay, has such a catalog and informs us that the surface gravity on Dagobah is 0.9 G, so it's 90% of Earth. All right, so we can figure out then that G on Dagobah will be 9.81 times 0.9. Okay, that'll tell us what our G is for this. So 9.81 times 0.9. All right, so we got 8.829 as our acceleration due to gravity. All right, so if we have the X-Wing's mass and its lift rate, okay, we can calculate its peak power output by going force times speed. Now, what force are we working against? Gravity. Okay, so normally we just go m times g, but g is 9.81. We need to use g on Dagobah. Okay, so that's going to mean that we're going to take the 5,600 kilograms, okay, and multiply it by 8.829, and then multiply that by the speed we calculated, okay, 0.4. All right, so Yoda is rated at 19,776 watts. Hey, that's impressive. Okay, okay, it's about 25 horsepower. Not bad if you're little and green. Okay, a horse is obviously a lot bigger than that. Okay, so it's about the motor of an electric model smart car, something like that. Okay, so there's Yoda in the smart car. So at current electricity prices, Yoda would be worth about $2 an hour. Yeah. Okay. But remember that moving stuff around is only one of the ways that force powers were demonstrated in Star Wars. Okay. The Emperor like zapped Luke with the Sith lightning. Okay. And that's to make electricity arc through the air is like an exponentially larger amount of power. Okay. So that would be somewhere in the range of like megawatts and stuff. Okay. So anyway, okay, that's kind of what we're looking at there. So that would be about 400 watts for Luke, okay, when he's like pulling the lightsaber toward him. That would be about all that takes, okay. But Yoda's at 19 kilowatts. So yeah, if we had Yoda there and he was, standing in front of these, windmills, then he could go, rotate your wheel, okay, and get some power going. I don't know if he could really do that or not, but okay. Okay, so if we're looking at this here, what would a free body diagram, because this is a good review of free body diagrams for our test on Tuesday, okay, what would a free body diagram of Yoda lifting this thing out of the water look like? What are some forces we might need to consider for our 5,600 kilogram X-Wing? What's the most obvious one? Gravity. Okay, and the other obvious one? Yoda. Okay, so those are the two obvious ones. Okay, Yoda and gravity. What else is in there? Something's in the water. What does water do to it? Well, it depends whether there's air trapped in it or not. We would have to assume that air would have been trapped in the spacecraft, right? I mean, it's sealed to travel in the vacuum of space. It would have to be airtight. Okay, so there would be air trapped, and air starts with B. Buoyant, yeah. So there would be a buoyant force that would also be assisting, okay, here, but moving something through the water. Easier or harder than moving same thing through the air? Harder, okay, because there's water resistance, okay, in other words, friction, okay, that's going to be opposing as well. All right, so again, remember, this is that thing that we said is kind of the toughest thing in the unit, is being able to visualize the situation and identify the forces that might be acting. Okay, now question number 3 is another one that's good for an energy review thing here. Obviously, it takes energy to lift the X-Wing out of the water because we're increasing its potential energy by pulling it from, under the water to above the water. But when Yoda moved it horizontally, okay, assuming that it moved at a constant speed, which it seemed to, okay, how much work does he do during the part where the X-Wing moves horizontally? Yeah, but we're saying it's moving at a constant velocity. So how much work did he do while he moved it horizontally? None. Okay, to move the X-Wing horizontally would have required no work because it didn't accelerate, so there was no change in kinetic energy, and it didn't get any higher or lower, so there was no change in potential energy during the time it moved horizontally. Remember, work is a change in mechanical energy. Yoda's already done the work. He's already lifted the X-Wing out of the water. Okay, to move it horizontally through the air wouldn't require any work, provided there was no friction, okay, which there would be, but okay, provided there wasn't any, that would take no work at all to move it horizontally. Okay? It's just like when if you pick something up, right, and you put it on your back, to walk around with it isn't hard, right? You're just moving around, but the lifting part of it, okay, that's where you change some energy. It's harder to do. Okay, that sort of makes sense. Just a little bit of opportunity to review just a couple of things there in kind of a fun way. So, all right, here is the plan going forward.